Yeah,
Although
that's good.
pretty tired of a wheelchair.
That would be too.
Yeah.
God, I can imagine.
Next week I may be able to start putting weight on my legs. So that's like, I'm really looking forward to that.
This week or
Next
when
week,
did you
yeah.
say?
Next week. I
Oh,
have a
next week.
doctor's appointment on Monday, and until then I'm not supposed to bend it or put any weight on it, which means, pretty hard to get around. But next
Yeah,
week,
naturally.
yeah, next week I may be able to start actually learning how to walk again. It's like,
Jesus.
which would be nice.
What?
Yeah, it's been a long 6 weeks, that's for sure. At least the weather's good.
I'm missing not having the normal lectures.
Yeah, me too. I really am also. I don't really like the pad at all. And yeah, it's not ideal. I didn't,
It's
I
not the
thought about
same.
converting everything into PowerPoint, but that sucks too. So yeah, there's just
Yeah.
a good solution. I kind of like the Blackboard. The reason I like the Blackboard is it makes me think really hard about what I'm trying to say. And and the important parts are setting up the problems, not actually doing the arithmetic. And so it's like
Yeah.
it makes you think about it that way. I don't know why. It's like the more I lecture, I realize it's not really, doing these little calculations, it's not really the issue. It's like the how you set up the problem, what are the variables, what are the coordinate systems, like those are all the important things. I mean, you could almost just
Yeah,
jump.
that's what separates it from that.
Yeah, it's like, all right, let's set up the problem. You could just like jump to the end and say, okay, now that it's set up, you can solve it. It's just like jump to the end because the arithmetic's not the important part.
Yeah.
But
Totally.
I don't know. This is my view on lecturing, but it's actually true in any topic.
Yeah, honestly, I usually find that that's the hardest part about physics is just understanding where you're going, not how to do it.
Yeah, yeah, right. Exactly. Yeah. And the pictures, like the, illustrations, they're super important. That's why my lecture notes are full of these little cartoons and stuff.
Oh, that's a big help. Yeah.
Yeah.
Otherwise, I would not know what's going on
I
at
know.
all.
I spend a huge amount of time. I really like making little cartoons. I have to admit, and it's really fun. It's kind of funny that I really like it, but yeah, they're important too. They're totally fun.
Speaking of which, actually, I wanted to say I thought the lab was pretty fun. This lab
Oh,
was
okay.
pretty
So
like
the
my lab
crushing
four.
foam one, you liked the crushing foam one?
Yeah, I did.
Awesome. Okay, take a look at lab
Um,
number 5 because lab number 5 is going to be even weirder. I'm happy to hear that. Yeah, tell me what you think because, I didn't love it because, I wanted to lock it down so that it didn't rattle, and then we would have had much cleaner data.
yeah,
Yeah. So,
that actually that became a problem during my thing because between like my fourth and fifth trial, which was thankfully a good place for it to happen, the whole thing just kind of came crashing down.
okay, yeah. So yeah, it's not
Now, between
really.
my oh
Yeah,
well,
so
between those two trials, I was going. I'm sorry, we've got like a delay, so we keep talking over each other.
oh, okay. Well, I'll wait for you to finish then.
Okay. Thankfully, it was between trials where I had already done all of the options once, and I needed to like do no foam, foam with inverted cork again. So it all worked out.
Okay, good. Yeah. Well, so I'm glad it worked. Yeah. So if you have something like it falls apart, that's a really good reason to discard data. You're allowed to discard data if you have a good reason, right? So even in like, a real scientific setting, you just have to give the reason. I remember once
Yeah.
grad grad student working with me, he was, in his lab notebook, he'd keep trial numbers. And when he wrote his paper, he said like he reported the data as trial number 37, 38, 40, and 41. And we were like, yeah, well, there's no reason to change these, nobody will be annoyed. I mean, we had a reason to discard the one that was in there, but it drove everybody crazy. It's like every single reader was like, wait, why did you discard that one? So in hindsight, I should have, it didn't occur to me that people would jump on it as if it was going to be something unethical. But every single person who read the paper just noticed that number 39 or whatever it was missing. It was crazy. So it was like the worst advice I gave him. It's like, yeah, whatever. I mean, you're allowed to discard a trial if there's a problem with it.
I mean, yeah, especially if it doesn't work at all.
So it caused them this massive hassle, for like ages. His
Yeah.
thesis defense, his qual, his publication. It's like every single person who read it jumped on this. It's like, it's kind of funny. Like, I didn't expect. Yeah. So, but yeah, there's no reason not, I mean, the reason he started it, I think, is he was trying to take complete data sets and one of the cameras, didn't trigger or something. It was like, it had a really obvious reason why he discarded. But
Weirdly enough, when that happened, lab was like about to end, and I was like, okay, kind of time to go. So I raised it up back to where about I thought it was, and kind of took the rest of my data. I got it really close, but only slightly high. And yet I still found that the force read was about the same.
oh, okay, odd, but interesting.
So I mean, I must have gotten it pretty close, but
Yeah, interesting. Well, I'm glad to hear that lab worked. So yeah, so the next lab, which is after Thanksgiving, we ordered a bunch of weird stuff for you guys to play with, but you can bring in any elastic or rubbery object to try and explore. But the lab will be challenging because you have to figure out, what do I want to do? So probably the first hour you're going to be like, what experiment should I run, and is it going to work, right? So that actually takes time. So that the last lab is going to be hard for that reason. Because I'm not saying do this experiment. You have to like decide, what experiment do I want to do and how do I get it to work?
well, kind of like lab 3 though.
Yeah, exactly. Well, lab 3, yeah, the bouncing ball one, but yeah, that's right. You have to figure out how to get it to work. New software and microphones and everything. Yeah, right.
I kind of knew what I was doing for that one. Then after a while, I was like, all right, I'm just going to start taking data that I think applies to what I'm talking about. And lo and behold, that ended up saving the lab a little bit.
Yeah, lab number 3 is amazing because you get really precise measurements with audio.
Yeah.
So I really like lab 3. I mean, we've run lab 3 now more than 1 year. It's been good every time we've run it. So that one is a good one. It's like not too hard to set up, and you get amazing precision. It's like, so with like simple, well, easily available software, you get amazing precision, which is like, how rare is that? It's pretty amazing. Yeah. Okay, what time is it? Oh wait, we should be starting lecture. Haha, it's way too more fun to just chat, isn't it? Okay, so let me find my pen here and whiteboard. So are there any announcements? Yeah, so you guys have a rough week again this week because you have lab due tomorrow on the foam crushing experiment. So I've heard mostly good comments about that lab, but that doesn't mean everybody had a good experience. So yeah, give us your feedback on that. Mainly what my feeling about that lab is, it would be nice to have some clamps so that we could lock down the track, the side of the track that's getting hit, so it doesn't wobble as much. So yeah, I think that's on the list of things maybe for next year. Wait, lots of clamps. Right, so on that note, Monday is a potential makeup day for labs. So if you want to get into the lab, let Zach know. And then after Thanksgiving, you'll have the 5th lab. And the 5th lab, the idea is to look at elastic or rubbery things and try and see if you can learn something about the force displacement law. So I gave some suggestions on experiments you could do. And we ordered a bunch of stuff like balloons and little squishable toys and stuff. But you can bring in whatever you want to experiment on. So, but the hard part of lab number 5 is going to be decide what to do. So that makes it more challenging than the previous labs where we kind of tell you or suggest what to do. This time you have to design your own experiment. And so, I encourage you to focus on like one thing. Don't try to do 10 experiments. So, but then you're going to have to figure out, well, what do I want to measure and can I do it, right? So the first part of the lab will be challenged because of that. You could bring in something rubbery like a balloon. You can bring your own stuff in, lycra, anything, something rubbery. Something that's going to be a little bit more interesting than a classic spring, right? Because, we learn about classic springs, but real objects don't always behave like classic springs. So that's lab 5. And I think that's all for announcements, right? Okay, good. So we can move on to lecture. So last lecture, I hinted that we were going to talk about stability. And so the picture I'm going to draw is this, where you've got this guy. And of course, he has a little hat. And let me see if I can draw him properly. Actually, usually your leg bends this way, and then he has 2 arms and he's holding on to a bar, and this is a tightrope. And so the idea is by the guy walking on the tightrope can balance without falling down. And so why does he have this thing, this bar, there? Well, the reason he has this bar is he kind of increases his moment of inertia, and that helps him be more stable. So oops, let me get rid of this because I'm having trouble seeing it. Okay, so yeah, so why does that help him be more stable? So let's draw. So the actual problem is he's kind of like he's an inverted pendulum. And so when you think about a pendulum that's upside down, I want this to be straight. And there may be a mass up on the top here. And in this case, this is the center of mass. And this is the pivot. So this is an equilibrium point because if it's perfectly upside down, like perfectly vertical, he's not going to fall. But if he's very slightly tilted to one side, then he's going to start to fall over. And so the guy on the tightrope, what he's doing is he's adjusting his weight so that he keeps maintaining balance. If he has to adjust his weight really fast, then it's really hard to maintain balance. And so what's really relevant in this problem is how long it takes him to tilt over. So let's think about the inverted pendulum now. But now we're going to tilt him over. Let's change the color here. I'm going to tilt him over a little bit. And so we have mg down because of gravity. And then there's this angle theta there. And the height of the center of mass from the pivot point we'll call h. So, so the torque, which is r cross f, but f is gravity, we apply gravity at the center of mass position, is going to be mgh. So this is the force, that's the radius to the center of mass position. And then at small angles, it depends on the angle. So it would be sine theta if the angle was large, but in the small angle limit, it's theta. And we set that equal to I theta double dot because torque is the change in angular momentum, and angular momentum is I omega, and omega is theta dot. So this is the moment of inertia here, and this is the angular acceleration. So this equation of motion, so let's rewrite this equation of motion. You can write it like this: theta double dot is equal to mgh over I times theta. So it's in the form of a second derivative of something, some constant. times that something. So this is similar to a harmonic oscillator, which is what I mentioned last time. So remember, a harmonic oscillator looks like mx dot is kx. It has a minus sign, and the solutions are sinusoidal. But if I change this to m double dot is equal to kx, then I have exponential solutions. So this system has exponential solutions. So let's look at that again. So if I have theta double dot is equal to mg h over I theta. Here's a solution. So that's an exponential solution. So let's see what it looks like. Theta double dot. If I take the derivative twice, I get alpha squared is equal to alpha squared theta. And so all I need to do is set alpha is equal to this, and I'll have a solution. So so what is this? And this tells you how fast he's falling over. So it's like, how fast? Anyway, can you state, I have a question. Could you mind restating how we obtain mgh theta? Right, so the way we did that is the torque. So let's draw the picture again. We have mg, and we have a distance h. So r is this vector h, and f is mg, and so r cross f. So if theta is really small, then r cross f is 0. So this is f, it's in the z direction. This is r to the center of mass position. So the torque, which is this component perpendicular, only depends, it's not the component, it only depends on the perpendicular component, is mgh theta. It's actually mgh sine theta when you do the cross product, but in the small angle limit, sine theta is equal to theta. Does that help? So I just computed the torque, and then I set it to be I times the angular acceleration. Okay, so let's look at the solution. So where did I get this? I just said, well, suppose at some particular time we have an initial theta 0, which is how far off he's tilted. Then we'll look at the solution. So if alpha is really big, then he falls over really quickly. And if alpha is really small, then it takes him a really long time to fall over. And so if I is big, then alpha is small. And that means he falls over really slowly. And the fact that, so when he falls over really slowly, that means that he has a lot of time to adjust. So yeah, so to do this problem more rigorously, you would describe it as a control problem. So in physics, we don't usually spend a lot of time discussing control problems. If you're doing robotics, you would, or then you would describe it as like, how much time does he have to change the angle, and how quickly should he change the angle to adjust so that he get back into the equilibrium position. But basically, it's easier for him to adjust and get back into the equilibrium position if he has more time to do it. And so that means if you have a bigger moment of inertia, you have more time to adjust to get back to the equilibrium position, and then you don't fall over. And so that's where this pole is. You make this big pole, and that means there's more mass further away from the pivot point, and that increases the moment of inertia. So you can see why having a big pole, particularly if it has weights on the ends or something, would help you stabilize, because you have more time to adjust to maintain stability. Okay, so that's basically the setting. Okay, so next example, tilting a spinning wheel. Okay, so let's draw a wheel. So I have a wheel. Here's my wheel, and I'm going to make it rotate this way. So if I have, so the fact that it's rotating this way means if I describe the wheel with an XY plane, then this would be counterclockwise with Z in this direction. So the angular momentum of this spinning wheel is in this direction. So supposing I now have some distance here, let's call this R, and then I exert a force F on my wheel. So L is in this direction, I already said that. And R cross F, so this is like R is like in the Z direction, and F, so if I do XYZ with the right hand rule, then I get torque in this direction. Just taking R cross F. So torque is change in angular momentum. So that means I have a, so let's think about in a time delta t, how would the angular momentum change? So so delta L would equal the torque times delta t. So that's exactly equivalent to torque is delta L over delta t, right? So remember, torque is the change in angular momentum per unit time, and these are vectors. So looking at this problem, if I exert this force perpendicular to the angular momentum, then delta L which is the change in angular momentum, is perpendicular to L. And so after time t, delta t, there'll be a small change in the angle of L. So that means the wheel is going to tilt its angle, but it's tilting in a direction you don't really expect. Like when you push it, it's going to move in a perpendicular direction. That's why wheels are kind of weird, because you push them this way, then they move that way. And that's got to do with the spin. So what's the size of this angle change? So let's call this a delta phi, because it's a change in the angle during time delta t. So we're applying the torque for a time delta t. That's where this delta t is coming from. So what's delta theta? Well, if delta L is small, then you can just think of it this way, as delta L over L. So remember, if you change something like this, then this distance is R theta. So that's where this is distance R, and so that's equivalent to this statement. Okay, so let's put in our value for delta L. So this is torque times delta T over L. And this is R F delta T over L, if we actually put in a force. So L is I omega for the wheel, where omega is the angular rotation rate of the wheel, and I is its moment of inertia. So I can put that in here too. Delta T over I omega. So this is the thing we want to look at. So if I'm applying some force F, how big a change in the angle happens over a small period of time? And this expression tells you that. But we can look at it and say, how does this depend upon the quantities in here? So if R is bigger than, even for a given force, then the torque is bigger. And so you get a bigger change in in the angle. So delta phi is how much the angular momentum vector changes in this time delta t. And so what is the angular momentum? So if you have a spinning wheel, the angular momentum is this vector perpendicular to the wheel. So if L changes direction, the wheel is tilting, right? So delta theta is how far in what angle that wheel is tilting its spin axis. So we are assuming the wheel is spinning around its, rotation, its axis of symmetry in this problem. Okay, good. So looking at this expression, if R is bigger, we get a bigger angle. If F is bigger, we get a bigger angle. If I is bigger, that means the moment of inertia is bigger, we get a smaller angle. So that means if there's more mass concentrated in the rim, like it's actually a wheel with all the mass in the rim, then you get a smaller angle. So it's harder to tilt the wheel over with particular force. And if it's spinning faster, this omega is on the bottom here. If it's spinning faster, then you get less change in the angle. And so supposing you have something that you don't want to change direction, like a spacecraft, then you could put a gyroscope in it and it would be really hard to tilt it. So if you put a gyroscope in it, and spin it really fast, then it's really hard to tilt. So you can see how a gyroscope would be something that would stabilize something and keep it from tilting. So same thing with like scooters, people put gyroscopes and spin them up really fast on purpose so that they're more stable and less likely to tilt. It just requires a bigger force to tilt them. So yeah, so to summarize, let's see. If a wheel is spinning fast, quickly, it is harder to tilt. So, if you ride a bicycle, it's kind of obvious. While you're starting up, it's easy to fall over. And once you get going, harder to fall over. It's the same analogy. Same with the bike. Biking. It's once the wheels are spinning, you're pretty stable. It's and again, its stability is like how long does it take to tilt over? Because you would fall over with gravity eventually, but it's like you have more time to adjust. Okay, so let's move on to the next topic, and that's conservation of angular momentum. So we talked about conservation of momentum when you have internal forces in a multi-particle system and they're equal and opposite, then total momentum is conserved. And so we're going to do the same type of thing, but with angular momentum now. So suppose we have n point masses, and so we can give a mass mi, and they have positions xi, and they interact with forces fij. So fij would be the force from particle I onto particle j, and then the total change in momentum, or actually that's not what I meant. Let's look at the change in momentum of one particle. It would be due to all the forces on it. So that means all particles j that aren't the same as particle I, fji, like this. So this is the force from particle j onto particle I. So what's this? This is change in momentum of particle I. It's just the sum of forces on it from all the other particles in the system. So so let's look at the total angular momentum of the whole ensemble. L is going to be the sum over all the particles of xi, those are the particle positions, cross pi, those are the particle momenta. And you have to pick an origin for this because the position once you have the the angular momentum depends on what origin you pick for the problem. So now let's take this and we're going to take the time derivative of this thing. So dl dt. So if we're trying to show that L is conserved, we just have to show that dl dt is 0, where we've summed up the angular momentum of all the particles. So yeah, so let's take the time derivative of this. Right, okay, so we can do this dxi dt cross pi plus what am I doing here? Xi cross dpi dt. Okay, this term goes to 0 because dxi dt is velocity, and velocity is always in the same direction as momentum. So we don't have to worry about this term. So this is the only term we have to worry about. So let's write this now using this formula. Xi cross the sum of j not equal to I of f ji. So that's a function that describes the total angular momentum. So let's look at, so I'm going to move this over to the next view graph. Let's write it again so we remember what we're talking about. J not equal to I of f ji. So let's consider a pair of particles. So this, we've summed over I and we've summed over j. So there are two terms for each pair of particles. So you can think of all the forces for each pair, and then you get the force from particle I on particle j and the force from particle j on particle I. So so in this sum, we'll have this term, and we'll also have xj cross fij. So those are the two terms that are going to come for each pair. But if you have equal and opposite forces, then fij is equal to minus fji. And so you can write this as xi minus xj cross fji. So what are the conditions for this to be 0? So this is the vector in between I and j, and this is the force exerted from one to the other. So like with gravity, if you look at the force actually depends on the direction between the two particles, and the force is in the same direction, right? So you always, the force is actually along the direction connecting the vector connecting two particles. And the same thing's true for electrostatics. So in many situations, it's actually true. So for gravity, electrostatics. So if the force is parallel to the direction, why does this keep doing this? So this is direction between the particles. Then this thing equals 0. And so that's for every pair of particles. And then because this sum actually, you can think of the sum as covering all pairs of particles because you're summing over I and j. that implies that dl dt equals 0. So as long as all forces are internal forces, and in this case, the particle pairs, the forces are oriented along the vectors connecting the particles, then you're really assured that angular momentum is conserved. So, so one thing that's subtle is that, well, this is generally true, and most forces like gravity, and internal forces inside bodies do obey this. Simulations don't always obey this, and so if you force your simulation to obey this, you're assured that angular momentum is conserved in the simulation. But but there are certain popular simulation techniques that don't obey this criteria. So one example is SPH simulations. So they compute forces by averaging over properties of particles with a kernel, and so SPH stands for smooth particle hydrodynamics. And so it's difficult if you're trying to do a spin dynamics simulation over where you have a long period of time where you actually would care about conservation of angular momentum, you might have a problem. But if you do all pairs, all force pairs equal and opposite aligned along the direction between particles, then you're assured that angular momentum is conserved. So you can design a simulation with that in mind if you want to do long-term spin dynamics simulation. Okay, so that means we've shown for internal forces, and we have this satisfied. Angular momentum, the total angular momentum is a constant. Okay, so let's move on to the next topic. We have a question. If the force is not parallel to the direction, this means there's an external force or torque. Well, yeah, so an external force could certainly exert a torque, right? So then you'd have to figure out what it does. So like, an external force would be like gravity on the wheel or gravity on the tightrope walker, and that definitely gives you a torque. Yeah. If you have internal forces, can they violate this? So that's a good question. Like, what if I have dipoles or something? Well, dipoles, you can usually write them out as sums of forces that obey this. So most physical laws are designed to depend on the vector between things. So usually you expect the laws of physics to obey this. Angular momentum should be conserved with internal forces. Okay, so let's move on to the next topic. So we're going to do some orbit stuff. Yeah, so let's talk about Kepler's first law. So what's Kepler's first law? So Kepler's first law is orbits or ellipses. And there's a little bit more to it. The sun is at a focal point. Of the ellipse. So, if you have an ellipse, you can always describe it as, so an ellipse is something where the distance when you add up the distances to two focal points is constant. And so it's a conic section. And with Keplerian orbit, the sun is actually at one of these points. So, that's pretty amazing that you get some pure mathematical object out of Keplerian motion. So yeah, so we've already showed that angular momentum is conserved for essential force law. So and in particular, the component of angular momentum is perpendicular to the orbital plane, and that comes from the fact that if I have a vector so we'll put the sun here, sun. Let's actually write it so you can read it. Sun. And then here's my planet or my satellite. And the force is along R. So since R cross F is equal to 0, because the force is along R, that means that the angular momentum, so that's the torque, right? That means that L, which is R cross V times M, is a constant. And this follows because F is perpendicular to R in the central force problem. So angular momentum is constant. So let's look at the energy of the particle in an orbit. So energy is kinetic energy plus potential energy. And so I can write E over M is equal to 1/2 mv squared. That's the got rid of M. Let's get rid of M. V squared. So this is kinetic energy divided by mass minus gm over r. So remember, K in this case is 1/2 mv squared, and U, which is the potential energy, is this. And I'm assuming that big M is not moving here. So I'm not doing the two-body problem. We're just doing a really low mass in orbit around a really big mass. So that's potential energy. And so it's kinetic energy per unit mass plus potential energy per unit mass. And so now let's say in the orbital plane. The orbital plane, I can write the velocity as the sum of two components, a radial component and a tangential component. So yeah, so V squared is VR squared plus V theta squared. And angular momentum is R cross V. And I'm going to do it per unit mass. And I need to make sure that's clear here. So usually I have an issue. I have a problem with my notation here because people usually do everything per unit mass and then just call it L. But I have to be a little bit careful because in the physics sequence, usually we assume L has the M in there. Same with E. But in orbital mechanics, because the little m drops out, you usually just ignore it. So L over M is R cross V. So because so in the orbital plane, so I'm going to ignore anything out of the orbital plane here. We only want the component of V that's perpendicular to R. And so this is equal to R V theta. If I take the, so let's just take the magnitude of it like that. I don't really need to put this here. R V theta. So that means I can write V theta squared, which is this thing, is equal to L squared over M squared over R squared, like that. So that's nice. So now I'm going to put that in here. Let's write the energy again. Energy per unit mass is equal to 1 over M K plus U. We already wrote that. But let's do this again. 1 over M. We have 1/2 VR squared plus 1/2 V theta squared minus GM over R, which I can write like this. Why did I do that? That's not right. It's another error in my notes. Let's get rid of this. We don't need this. Get rid of that. Okay, 1/2 VR squared plus L over M squared divided by 2R squared minus GM over R, like that. So VR is dr dt. And this, so this depends on R, but L is conserved. So what we have now is an energy that depends on dr dt. So let's make that clear. So we have dr dt squared plus two functions of r. So this is a function of r. So once you choose L, you can describe the energy as change. It's like a radial motion plus a function that depends on r. So so what people do is they give this function a special name. This thing is called the effective potential when you think about radial motions alone. So we can think about the problem as a one-dimensional problem where we're only allowed to move in radius. And so let's consider oscillations in radius alone. Then the total energy is conserved, angular momentum is conserved, and so that determines this function, which is called the effective potential. So let me just write it up here. So this is E over M. I'm going to erase this because we've got it already. So U effective is equal to L over M squared over 2R squared minus GM over R. And this is an effective potential. So I could only think about how the motion is in radius once I choose the angular momentum. So let's draw some pictures now to kind of give you a feeling for what that means. So I'm going to make an axis of energy per unit mass. And then we'll have R here. So let's put in, this curve is L over M squared over 2R squared. So that's the term. So remember, let me write down the effective potential again. L squared over M squared over 2R squared minus GM over R. So I just plotted this term here. Now let's pick another color, and I'm going to plot the minus GM over R part. So when I take this one plus that one, what you get is something that looks like this. Without those squiggles. So this is the full potential. This is U effective of R. So now once I've got the full potential, I can think about the things that we did before. So remember, we have energy is kinetic energy plus potential energy is a constant. And so that means when you have a particle moving around, it's increasing in potential energy, decreasing in kinetic energy, and vice versa as it moves in the orbit. And so what if I put a particle here right at the bottom of this? So started off at this minimum in the effective potential. Well, if it's at the minimum, I can't ever, the energy is equal to the potential energy and the kinetic energy has to be zero. And so the particle has to stay at that radius. And so this particle here is a circular orbit. So on this plot where I plot the effective potential as a function of radius, so remember, I had to choose the angular momentum to do this. But once you choose the angular momentum, you know the energy of a circular orbit and the radius too. It's like all set. So what if I start a particle up here? So with this energy, so it's the total energy per unit mass of the particle. Well, this particle has a minimum radius it can get to, but it can go out to infinity. So you can think of this particle as coming in and then it gets to some minimum and then it has to turn around and go back. So this is a hyperbolic orbit. So what they look like is they look like this with the sun in the middle. So lastly, we can pick an orbit like this, and that's an elliptic orbit. Oops, I managed to erase it. Let's do it again. There. So if you pick a particle, pick an energy like this. So one thing I did not draw was 0 here. 0 has to be kind of here like this. That's 0. Or actually I did draw it, it's just erased. Okay, so there's when you have negative energy, this is an elliptic orbit. So the orbit's an ellipse, and the energy goes is constant, but the radius can go to a minimum point and a maximum point. And once you pick the energy, actually, you can figure out set the kinetic energy to be 0, and then you're at this point or this point, right? And so you could figure out what the radius of the minimum radius is and what the maximum radius is. Once you specified energy and angular momentum, you can compute the minimum and maximum radius. So those radii they have fancy names. They're called perihelion or aphelion if it's going around the sun. They could be called perigee or apogee if it's in orbit around the Earth. You can just call it pericenter or apocenter if you don't really want to specify what it's in orbit around. So let's draw that. I'm going to erase this so I can draw an elliptical orbit. Elliptical orbit looks like this. And this point here would be pericenter, and out here would be apocenter. Apocenter. So one thing that's special about pericenter and apocenter is, they're at the maximum. So at apocenter and at pericenter, the radial velocity component is 0. So VR has to equal 0. So that means if you know the energy and the angular momentum, you can figure out not just what radius it is, but you can also figure out what v theta is, because you'll be able to know why is VR 0. So VR is the radial, the rate and change in radius. So if it's at the minimum, the rate of change of radius is 0. Otherwise, it would be going in or out. And it's like at the minimum, so it's coming down, and then it settles out, and then it goes back out again. So it's a minimum or a maximum, right? Yeah, just at that moment, the radial velocity component is 0. But it's useful to remember so there's a problem on the problem set where it's handy to remember that VR equals 0 at apocenter or pericenter, because it lets you solve for v theta, for example. What about when the radius is between? Yeah, so the energy's fixed. Where's the energy go? So remember, like in a spring, we have this balance between kinetic energy and potential energy. And so the total energy is fixed. But, if it's closer in, you have more potential energy. Although the effective potential has got this kind of shape, kind of more complicated shape. But so think about what's going on at the bottom of this dip in the potential energy curve. It's somewhat like a harmonic oscillator. Remember, harmonic oscillator, the potential energy looks like that, and particle goes back and forth in the potential well. So it's potential well. So here the effective potential looks like a potential well. We have oscillations in radius. So sometimes people call those epicyclic oscillations, because you can think about if the orbit is nearly circular, you can think about just oscillations at the bottom of this potential well. And mathematically, it's just like a harmonic oscillator. So energy is going between potential energy and kinetic energy, with the total being fixed. So hopefully that'll help you think about the problem. This is why we draw plots like this, right? That graph. So the graph that I showed you, I showed you on this graph, this blue curve is the effective potential, which is, it's like, if I'm only thinking about the radial degree of freedom, I can think about this problem as oscillations in radius. And so this blue curve is the effective potential for the radial motion. And the black curve was the part that came from the angular momentum, and the green part was the part that came from GM over R. And then when you draw these red lines, those are like total energy. And then, so you can, taking into account only the radial part of motion, total energy is conserved, but kinetic part is only the radial part. And so with these red lines, when total energy conserved its kinetic part, but only the radial part, because the kinetic part only has the radial part, because we sucked up the tangential part into this effective potential. And the reason we could do that is angular momentum is conserved. So with that in mind, kinetic plus effective potential is conserved, total energy is conserved, and you have a balance between the radial component of kinetic energy and the effective potential. Does that kind of help explain what's going on here? Yeah, hopefully that makes it a little bit more clear. Okay, good. So yeah, so I didn't actually show Kepler's third law yet, or is it first law? It's first law, not third law, it's first law. So how do you prove that? So yeah, so let's do that. It's a little bit of arithmetic, but here, so let's look at the radial equation of motion. So R double dot is equal to the minus du effective dr. And that, so now I have to take U effective. So let's write down what U effective is equal to L over M squared over 2R squared minus GM over R. So I have to take the derivative of the effective potential with respect to R. And you get this. So this is kind of hard to solve, but there's a trick that lets you solve it. And the trick is you set U equal 1 over R, and you do a variable change to U. And when you do that, you get du dt is equal to U dot is equal to minus R dot over R squared. And that you can write as du d theta times d theta dt. And using the fact that L is equal to R squared theta dot, you can write du dt is equal to du d theta times L over R squared. And this is L over M. This is L over M. Okay. And so using these and this, so this is like a bunch of arithmetic. But once you do that, you can regroup everything, and what you get is a whole bunch of arithmetic that is in my lecture notes in case you're interested. But I'm skipping a few steps here, so that's what this big arrow means. Let's change color. Why not? You get this. You get that. And this, so this is now an equation for U, which is 1 over R. So it's a second order differential equation for U in terms of theta. And this turns out you can solve it pretty easily. And so the solution is this. P to the minus 1. And this is, so this is a general solution to that previous equation. And it has two parameters that describe it. There are two free parameters. One is E, the other is P. And P is equal to L over M squared over GM. So that depends on the angular momentum and GM. And E is equal to the eccentricity. It's called the eccentricity. So now, so remember u is 1 over r, and so we can rewrite this equation. And I'm now it's like change a variable. I'm gonna make a new angle. It's the same thing as theta. In convention, people usually call it f. And it looks like this: p is equal to 1 plus e cosine f. So the Keplerian dynamics, it's got like 300 years of history. And so there's all sorts of weird vocabulary associated with it. So the f is the same thing as theta, but it's called the true anomaly. And an angle that gets called anomaly means that it's with respect to pericenter. So you get 0 at pericenter typically. So that's opposed to an angle called a longitude, which is respect to the equinox direction, which I think is the fall equinox direction. So all the angles for orbits in the solar system, they're either longitudes or anomalies, or there's something else. And the vocabulary is super old fashioned because it was, started a couple hundred years ago. So, but in any case, so looking at this, so this is now an equation for an orbit, and it gives you the radius as a function of angle. And this actually is the equation for an ellipse. Yay. So, and so that we can ask some more things. Well, so once we have an ellipse, we can ask, well, what's the minimum radius? Well, if I set f equals 0, I get the minimum radius. So that will give me the closest distance, the pericenter distance. If I set f equal to pi, then I'll get the maximum radius. And so if I add the maximum and the minimum radius together, you get what's called the major axis. How did we get RF again? Yeah, so I skipped some steps, but essentially you start off with a radial equation of motion, and then you do a variable change where you go from r to u, which is 1 over r, and you use the fact that you can use u dot and relate it to d theta dt with the angular momentum, so that you can, instead of having an equation for time, you have an equation for how u changes with theta. So here's another subtlety. You can solve this equation to get the shape of the orbit, like r of theta, but you can't, and there's an analytical solution for it. There's no analytical solution for r as a function of time. So that's part of the trick here to show it's an ellipse, is you have to get away from r of t. And you have to convert the equation into r of theta. And I know this is a bit technical because it's like Keplerian stuff, which may not be useful for most of you guys, but I thought you should see at least a little bit of orbital mechanics in the class. So yeah, so we skipped some steps, but if you're curious as to the full derivation, I did put it's in my lecture notes, and it would be in other mechanics textbooks that spend time on Keplerian motion, which is sometimes neglected in introductory mechanics. Okay, so let me draw this picture of an ellipse again, because here's an ellipse. So here are the two focal points. One of them is, where r is respect to, with one of them, I can figure out where r is a minimum and where r is a max. And so here is r min, and here is r max. And if I take r min plus r max, I get 2a, where a is what's called the semi-major axis. So if I put a point in the center of this ellipse, the major axis is the peak to peak, the largest in the largest direction, and the minor axis is the distance from one side to the other on the shorter direction, and the semi-major axis is this distance. So so the minimum radius is when f is 0, and the maximum radius is when f is pi. And so you can figure out what these are in terms of P. And sometimes what you'll see people do is so like, how do I write P in terms of the semi-major axis? So you can do that if you solve for the minimum radius and the maximum radius. So I'll show you what they are. Turns out this is true. That's just setting f equals 0. R max is P over 1 minus E. And then 2A is R min plus R max is equal to 2P over 1 minus epsilon squared, or E squared, not epsilon squared. And that means that P is equal to A 1 minus E squared. And so you can also write the function for radius like this. 1 plus E cosine F. So this is another equation for the orbit. So what's the energy of the orbit? And so I'm not getting yet more arithmetic, right? But it can be handy to know what the energy of the orbit is. And it turns out it's this. So the semi-major axis determines the energy of the orbit. The angular momentum does not determine the energy of the orbit at all. And the angular momentum of the orbit does depend, is sensitive to the eccentricity. And so the angular momentum of the orbit turns out it's like this. So this is the energy of orbit, and this is the angular momentum. So if you want to, you could figure out if I gave you the energy and the angular momentum, you can invert these equations, figure out what the semi-major axis and the eccentricity are, or vice versa. If you know the eccentricity and the semi-major axis, you know the energy and the angular momentum. And in fact, the orbital energy does not depend on the angular momentum. So it's total orbital energy. So more subtly, the orbital period only depends on the energy. It doesn't depend on the angular momentum. So that's a little bit more subtle. So, and in fact, almost very little depends on any, almost all the properties of the orbit are constant. The orientation of the orbit, the eccentricity, the semi-major axis. So these all wind up being conserved. The orientation, the tilt of the orbit. All of these things wind up being constant, which is telling you that Keplerian orbits are have these special symmetry properties. So I don't know if you get into that. They wind up with lots of conserved quantities. Okay, so that kind of gives you a very rough introduction to Keplerian orbits. Okay, so let's do a more concrete example that involves angular momentum and torque. Yeah. Okay, so the example I'm going to do now is, okay, oh wait, I just noted a question. What does effective U means is still confusing. Okay, so let me, let's see, how do we explain that? I guess in terms of somewhat repetitively. Yeah, so think about the orbit. So really we have just think about orbit in the orbital plane. The fact that we've got conserved quantity, the angular momentum, means that you can use that fact to take a two-dimensional problem. So it's really an orbit in two-dimensional problem and describe it as if it were a one-dimensional problem. And that's taking into account only the motion, the radial motion. And when you do that, you can talk about kinetic energy is only taking into account the radial part, and a potential energy that only depends on the radius. So let me write that down again. So the energy is equal to a kinetic term plus a potential term. But if we have motion, the motion in radius, we write this as 1/2 m r dot squared. So that's the radial motion in radius, this kinetic energy only taking into account the radial motion plus u effective of r. And the u effective is usually done per unit mass, so I'll multiply by m. So this whole idea of this effective radius is how to describe this motion in this two-dimensional orbit, which actually depends on r and theta. And we're just talking about the radial component. And we can map it to a one-dimensional problem where you only have variations in radius. So that's where you get this effective potential term. And the only reason we can do that is angular momentum is conserved. So that's why it's thrown into the angular momentum part of this lecture notes. Does that help make it a little bit more clear? Hopefully. Okay, so I need to get out of this and then get back in because I'm out of slides. So let's do it again. So we have a little bit of time. So last example is the beetle on the Lazy Susan. So what's the problem? So the problem, I have this thing that can spin. There's a pivot point here. So this is this Lazy Susan thing. And this thing is initially spinning with some angular rotation rate, omega 0. And there's this little beetle, some feelers, and he's at a radius r from the center of the Lazy Susan. So this is the pivot point. And the beetle is moving at a velocity v that's tangential. So right. So we have, so let's write down all the quantities. So the Susan, the Lazy Susan, has, which is this basically a spinning disk, has mass m, and it has radius r. So I'm assuming the beetle's kind of at the end. And that means it has moment of inertia. Well, I didn't really tell you what its moment of inertia is, but it has moment of inertia I, and it's rotating around the center. And then the beetle, with an extra e here, the beetle has mass little m. And he has an initial velocity v, and the beetle is at radius r from the center, so he's right on the rim. And the Lazy Susan is initially rotating at omega 0. And this velocity v, what inertial frame? So v is with respect to the outside viewer. Okay, so so that's the initial condition. And then the question is, so what happens? The beetle stops. And when he stops, he's like slowing himself down by, like, exerting friction on the Lazy Susan. So it's an internal force. So when we think about the total angular momentum of beetle plus Lazy Susan, it should be conserved. So, so the question is, we have two questions. What is the angular rotation rate afterwards? So when we say the beetle stops, that means he stops with respect to the lazy Susan. So his velocity becomes the same as a point local, wherever he is on the lazy Susan. So we want to know what the angular rotation rate of the whole system afterwards. And then the second question is energy conserved? Okay, so to answer that, we're gonna so let's keep the picture. We just need to compute the angular momentum. So let's figure out what the initial angular momentum is. So the initial angular momentum is mvr, that's the beetle, minus I omega 0. So why did I put a minus sign here? Because the angular rotation rate is clockwise instead of counterclockwise, but the beetle is moving in this clockwise direction. So I just kept track of the signs that way. Now afterwards, the beetle is now moving at the same speed as the lazy Susan. So the angular momentum afterwards is this. So here the omega is actually the angular rotation rate of the whole thing afterwards. And I'm keeping the sign so that omega would be positive if it's going counterclockwise. So so I can just solve for omega using this. So in fact, so that answers part A. Part A is answered. Okay, what about energy? So energy. So the initial energy is the kinetic energy of the beetle, which is 1/2 mv squared, plus the rotational energy of the lazy Susan, which is that. And afterwards, we have m, and the velocity of the beetle is now the same as the velocity at the outermost radius of the lazy Susan. So it looks like this. And the rotational kinetic energy of the lazy Susan is that. So, but we had an expression for omega, and so we can actually compare these two things. And so if we take E1 minus E0, which is delta E, and we use our previous expression for omega, what you find is this is true. I plus mr squared v plus r omega 0 squared. So this is positive, and so this whole thing is less than 0. So so there's energy lost, which in hindsight maybe isn't surprising because the beetle actually had to come to a stop. So it's like beetle reduced the relative kinetic energy. So that's exactly like having one of these problems where you have something collides and sticks, right? So you reduce the relative kinetic energy, and that reduces the total energy. So we have a question is, why is omega and omega 0 different? So I defined omega 0. So we go back to the previous thing. Omega 0 is the initial angular rotation rate of the lazy Susan, and omega is the final angular rotation rate of the lazy Susan. So we had two different definitions. So that's what the difference is. Why does it change? Yeah, so because the beetle has some angular momentum. So the beetle is initially moving, and then it stops with respect to the lazy Susan. So it changes its velocity. So the beetle's angular momentum affects the whole system. The angular momentum of the whole system is conserved. So these are like internal force. So when the beetle stops, it's exerting an internal force. So that means total angular momentum is conserved. That kind of makes sense. Kind of like what we did with momentum. If you have internal forces alone, total momentum is conserved. We have the same idea here, except we're talking about angular momentum. Okay, so that is the beetle beetle example, and our next things we're going to talk about are sticky impacts, and then we're going to talk about gyroscopes, and then that's going to end our discussion about torque. But we have a little bit more. Oh, and we're going to talk about quantization of angular momentum really briefly, but that's it. Going to be it. So next lecture we will end our discussion of angular momentum and torque. And so I guess that ends this lecture. So yeah, let's stop sharing. And I guess I'll see you guys on Thursday, unless there's questions.
Thank you.
See you guys on Thursday.